Assalamualaikum. Good day, everyone. So we continue our lesson still on the topic of Schrodinger equation, but this time we move a little bit advanced to the time-dependent Schrodinger equation. So it is just discussion about evolving Schrodinger equation with time. Eh? So we move from describing what a wave function is. Yeah, we have learned what a wave function is, psi, to asking how it changes with time. We know the psi already, the normal form of psi, or from the Euler form of psi. And now, this time, we need to ask, how does the wave function change with time? So this is the main job of the time-dependent Schrodinger equation, because we want to know at a certain time, how does a wave behave? The one that we have learned before is just a standing wave, a static wave. But how about in time? How does the wave evolve in time, with time? So we need this time-dependent Schrodinger equation. So in other words, this equation tells us how a quantum state evolves once we know the energy conditions acting on a particle. Now, for this chapter, I want you to see it as the quantum version of an equation of motion. In classical mechanics, we track position and velocity. In quantum mechanics, we track the wave function and how it develops in time. So two different things. Huh? In classical mechanics, we track position and velocity, just like we have learned during the kinematics chapter before, right? We track down the position, the x or y coordinate, and we track down the velocity, and we track down the acceleration, so on and so forth. But in quantum mechanics, we track the wave function, the psi, and how it develops in time. So we have psi, also the t. So let us take a look at the next slide. All right. We move. No. And this slide shows the bridge between the classical physics and quantum physics. In classical mechanics, energy is written using momentum and potential energy. In quantum mechanics, we keep the same physical ideas. Now, before that, why do we need the momentum and potential energy? So if we try to imagine the atomic bomb model, the previous atomic model that we have learned before, atomic bomb model, where at the center of atom, we have the proton and neutron. And the one that orbiting the proton and neutron is the electron. Now, the energy, the kinetic energy, if we look at the proton and neutron and the electron, the one that is moving only the electron. So in terms of kinetic energy, looks like the electron is the only subatomic particle that carries the kinetic energy. And it also has momentum. The one that is moving also has momentum, right? And beside that, this electron has negative charge. And at the center of the atom, we have the proton, which has positive charge. And there will be potential energy acting on this electron with respect to the positive charge of neutron. So the potential energy exists with the interaction of the electron with negative charge and the proton with positive charge. And besides that, if we have a neighboring atom with similar material, so the electron at the atom on the left actually feel or has certain correlation with the neighboring atom, which also has the proton and also electron. So this also creates potential energy, right? So that is why energy is written using momentum of the moving electron and also the potential energy that this electron could felt based on interaction with the proton in the same atom or from the proton or electron from the neighboring atom. So in quantum mechanics, we keep the same physical ideas. We also play around with the momentum and also potential energy, but we represent them differently. So the momentum and energy become operator. Remember, momentum energy comes from the moving electron. Only electron could be seen is moving. Actually, the proton and neutron also moving, but with much lesser velocity than that of the electron. So the momentum and energy become operators acting on a wave function from the electron. They become operator. The momentum and energy becomes operators acting on the wave function, which is psi before this. The important lesson here is not just a change of symbols. The real point is that quantum mechanics still respects the same physical quantities, which is momentum and energy, but it expresses them through wave behavior instead of particle trajectories. Now look at the equations which I'm showing right now. So we have the momentum operators from your bottom left part. We have the momentum operators, the one that I mentioned just now. Okay, in quantum mechanics, we use momentum operators to describe the evolution of psi or the wave function through time. And we have also the other one from the bottom middle one, we have the energy operators, which we will use to describe the wave function even further. So the energy, the total energy that we are trying to calculate, or the computer is trying to calculate, if we have this simulation, is based on the equation that I've shown you, E equals to P squared over 2m plus V in terms of X and also T. So this is the, sorry, the total energy is the sum of the kinetic. This is the kinetic part, this is the kinetic part, this is the kinetic energy, the P squared over 2m. And also this is the potential energy part. Potential energy, which comes from the interaction between the electron, and also electron and proton in the nucleus. Right? So the momentum, remember we have discussed this previously. The momentum would be calculated using P equals to h bar times K. H bar is reduced Planck constant. H is Planck constant. H bar is reduced Planck constant. And we have the energy reduced Planck constant times omega. And the reduced Planck constant is the h over 2 pi. Whatever the value the h is given, divided by 2 pi, you got reduced Planck constant. Look at the bottom right corner. I have a question over there. Why do we need the operators? So in quantum mechanics, physical observables become mathematical operators acting on a wave function, which is psi. The eigenvalue of the operator corresponds to the measured value. So I don't want to discuss this much because it is purely mathematics. We need to learn physical mathematics, which not even in our syllabus. So what I want you to understand is that not the derivations, not the mathematical parts of the quantum mechanics. I want you to understand how and why do we need these steps, and what about and how, what is the output of these calculations. The calculations, the computer can take over our place and let the computer do the calculations, and we need to analyze the final result. What can the final result tells us, right? Now look at these derivations. we just need to take a look at the derivations. The derivations could be very, very lengthy. I just want you to have the gist of how the derivation is going to be look like. So the calculation will be done by the computer. So for this derivation, I don't want us to get lost in algebra. What matters is the purpose of the derivation. Now we start from a wave-like description because quantum particles behave like waves. And then we connect that wave description to measurable quantities such as the momentum and energy. Remember, we have momentum, we have energy, P and E. P and E always about P and E. Quantum mechanics calculation always about P and E because the only moving is in Javanese, moving. Moving means oscillating, moving. I'm talking about moving. The only moving part, moving subatomic particles is the electron. So moving particles, we have momentum, and of course, it has connection with neighboring electron, the proton, which will give us the energy. The energy of potential and energy of kinetic. Kinetic energy because of the movement, and energy of potential based on the interaction between the electron and electron proton. So the first part of the derivation is really about proving that the mathematical wave function is not just a random curve. The curve that we describe or we draw last week is not just a random curve. It's purely contains mathematical wave function, which calculated by the computer. We don't really use our hands and eyes to assist the calculation actually. So it will take forever to finish up those calculations. So we need high performance computer. It is built in a way, that naturally carries physical information. The psi,